Metals are the foundation of progress, strong, versatile, and essential. Today, we'll uncover the science behind these remarkable materials and their impact on our world. Let's dive in and discover how metals born deep within the earth shape our technology, drive innovation, and connect us to a more sustainable future. From their origins in nature to their vital role in our lives, the story of metals is the story of elements.
Earth has three layers: the crust, the mantle, and the core. Now let's take a closer look at one of these layers, the crust. So, the crust is composed of solid rocks and minerals and also known as the outermost shell of terrestrial planet. Earth crust is further divided into two types, the oceanic crust and the continental crust. Oceanic crust, which extends 5 to 10 kilometers beneath the ocean floor, is primarily composed of basalts and is often referred to by geologists as sima, representing the silicate and magnesium content. In contrast, continental crust is predominantly made up of granites and is called shale by geologists, indicating its rich silicate and aluminum composition. The main idea here is that the two types of crust differ significantly in both their composition and terminology due to the distinct minerals they contain. You might be wondering how the Earth crust is connected to our discussion about metals. Now, let's find out as we proceed to the distribution of elements in the crust. The Earth crust is composed of a variety of chemical elements, making up only 1% of the planet's volume, with some elements being more abundant than others. The Earth crust is mainly composed of oxygen and silicon, which together form silicate minerals. Additionally, oxygen, silicon, iron, and aluminum are the most abundant elements in the Earth crust, accounting for 88.1% of its mass. Other significant elements include calcium, sodium, potassium, and magnesium, each contributing to various rock types and geological processes. The distribution of this element varies across different regions, resulting in the diverse composition of minerals and rocks found in the crust. This elemental diversity is what gives the Earth crust its rich variety of minerals, each with unique properties and uses. The distribution of metals in the Earth crust refers to how different metals are dispersed and concentrated within the Earth's outer layer. Metals like aluminum, iron, calcium, sodium, potassium, magnesium, and others are found in varying amounts in different types of rocks and minerals. This distribution is influenced by geological processes such as volcanic activity, sedimentation, and the formation of minerals deposits. Understanding this distribution helps in locating and mining this metal for various industrial and economic purposes. Essentially, it describes where and in what quantities metals are found in the Earth crust. Here are the statistic of the variety of elements that can be found in the Earth crust, and notably 7 out of 10 most abundant elements are metals. Their percentage of abundance are presented. What are the primary sources of metals? The two primary sources of metals are ores and minerals. Ores are raw materials used to extract and produce metals, as most metals are too reactive to exist in their pure form. Minerals are naturally occurring substances which have crystalline structure made up of repeating units of two or more elements. They are essential in forming ores and are also vital for regulating metabolic activities in the human body. In simpler terms, metal needs to be processed from ores, which minerals play key roles in both nature and human health. To provide more information about the sources of metals, I will let Mr. CANTOS and Mr. SILVA to take over.
Ores are one of the primary source of metals. So to provide you with more knowledge, let's begin with the first type of ores. Oxide ore. These ore contain metals in oxide state, making them require more energy to melt due to presence of oxygen. For example, oxide ores like hematite and bauxite form through processes such as weathering, hydrothermal activity, and intense leaching, which oxide metal-bearing minerals in oxygen-rich environment. Sulfide ore. A sulfide ore is a type of mineral that contains metal combined with sulfur, often extracted for its metal content such as copper or zinc. One of example of this galena, which is a lead sulfide. Halide ores. Ores that contain metals and halogens are rare in nature, with chloride ores being in the most common type of halide ore. An example of this carnallite, which is commonly found in Dead Sea. Carbonate ores. Ores found in carbonated form in nature primarily consist of metal, carbon, and oxygen. An example of such an ore is calcite.
Now let's proceed with how metals are found in minerals. One, native form. Some metals like gold and copper can often be found in native form, meaning they exist as pure metallic elements within the earth, not as part of chemical compounds. 2. Sulfide minerals. Metals like lead, zinc, and silver are often found in sulfide minerals, such as galena, sphalerite, and argentite. These minerals form through hydrothermal processes, where hot mineral-rich water flows through rock fractures and deposits metal-bearing minerals. 3. Oxide minerals. Metals such as iron and aluminum are commonly found in oxide minerals. Examples include hematite and bauxite. These minerals typically form through weathering and oxidation of pre-existing rocks. Carbonate minerals. Some metals like copper and zinc can be found in carbonate minerals. For instance, malachite and smithsonite formed through the reaction of metal ions with carbonate ions in groundwater. 5. Silicate minerals. Many metals including magnesium and lithium are found in silicate minerals. Olivine and spodumene are examples of such minerals which form in igneous and metamorphic rocks. 6. Halide minerals. Metals such as sodium and potassium are found in halide minerals like halite and sylvite or potassium chloride. These minerals typically form through evaporation of saline water in arid environments. To differentiate the two primary sources, minerals are pure or compound forms of metals, while ores are rocks that contain sufficient concentration of metals to make extraction worthwhile. How are geological processes involved in the distribution of metals? Geological processes determine where metals are found by forming and concentrating deposits. Magmatic processes concentrate metals like copper and nickel in cooling magma, while hydrothermal processes deposit gold and silver from mineral-rich fluids near volcanoes. Sedimentary processes precipitate iron and manganese from water and weathering and erosion. Release metals, creating placer deposits. Tectonic activity generates heat and pressure, forming metal deposits in mountain regions, leading to the uneven distribution of metal ores across the Earth's surfaces.
Now, we're going to proceed to the processes involved in the metallurgy of iron and steel making. But first, let's define metallurgy. What is metallurgy and its significance? Metallurgy is the branch of science and engineering that studies the physical and chemical properties of metals, their extraction from ores and their processing for various uses. Essentially, it's about understanding how metals behave, how they can be transformed, and how they can be used effectively in manufacturing and other applications. Metallurgy is crucial because it underpins modern industry, providing materials essential for construction, automotive, and electronic sectors. It significantly impacts the global economy through the extraction, processing, and trading of metals. Advances in metallurgy drive technological progress by developing new materials and enhanced properties. This field also supports sustainability through metal recycling, reducing environmental impact and conserving resources. Metallurgy plays a role in medical and scientific advancement, producing material for devices and research tools. The first process of metallurgy is the extraction of iron. This involves the process of converting iron ore into pure iron using a blast furnace. Here's a brief overview of the key steps. So the first one is mining. Iron ores such as hematite, magnetite, and limonite are extracted from the earth through mining. These ores are rich sources of iron and are typically found in sedimentary rock. So the next one is the concentration. The mined ore is then crushed and ground to release the iron particles from the surrounding rock. After this, the ore is concentrated using methods like magnetic separation, flotation, or gravity separation to remove impurities like silica, phosphorus, and sulfur. So the last one is the reduction. Reduction in the extraction of iron involves converting iron oxide or the iron ore into metallic iron using carbon or coke in a blast furnace. So this process removes oxygen from the iron ore, leaving behind pure iron.
We have two primary methods of steel production. The first one is the basic oxygen steel making. Basic oxygen steel making involves charging molten iron, scrap steel, and fluxes into a furnace, where pure oxygen is blown into oxidized impurities, resulting in high-quality molten steel. In the bus process, we start by charging a mix of molten iron, scrap steel, and fluxes, such as limestone, into a basic oxygen furnace. Next, pure oxygen is blown into the furnace at high pressure. This step is crucial as it oxidizes carbon and other impurities, transforming the molten iron into steel. Finally, the molten steel is tapped from the furnace, and the slag, which contains impurities, is removed, leaving us with high-quality steel. The second one is the electric arc furnace. The electric arc furnace uses electric arcs generated between graphite electrodes to melt scrap steel or direct reduced iron, followed by the addition of oxygen and fluxes for refining the steel. The electric arc furnace method begins with charging scrap steel or direct reduced iron into the electric arc furnace. Electric arc are generated between graphite electrodes, creating intense heat that melts the metal. This method is highly efficient and environmentally friendly. To refine the steel, oxygen and fluxes are added to remove any remaining impurities, ensuring the final product meets industry standards.
Secondary steel making. This refers to the refining process that occurs after the primary steel making stage, which usually happens in a basic oxygen furnace or an electric arc furnace. During secondary steel making, molten steel is transferred to a ladle where it undergoes various treatments to adjust its composition, remove impurities, and improve its properties. This includes processes like deoxidation, removing dissolved oxygen using elements like aluminum and silicon. This improves the steel's mechanical properties and prevents defects like porosity and inclusion. Alloying, adding alloying elements like manganese, chromium, and nickel to give the steel specific properties. These elements enhances characteristics such as hardness, corrosion resistance, and toughness. Casting, pouring the molten steel into molds to form ingots, billets, dooms, or slabs. This is the final step before the steel is rolled or processed into its final shape. The refined molten steel is poured into molds to solidify into desired shape like ingots, pellets, plumes, or slabs, which are later processed into final products.
Shaping and forming. It refers to processes used to manipulate metal into desired shapes and sizes. These processes typically involve applying force to the metal to change its structure without removing material, often by using heat and pressure. So they are shaped and formed through various processes such as hot rolling. The steel is heated and passed through rollers to form sheets, bars, or structural shapes. Hot rolling makes steel easier to shape while also enhancing its strength and flexibility. This process is widely used to produce steel products for construction and manufacturing industries. Cold rolling. The steel is further rolled at room temperature to achieve precise dimensions and improve surface finish. So, in cold rolling is a process where steel is further rolled at room temperature after hot rolling. This method achieves precise dimensions and a smoother surface finish, making the steel stronger and more uniform in appearance, ideal for high quality and refined steel products. Forging. The steel is heated and shaped using compressive forces. So, in forging is a process where metal is shaped by compressive forces using hammers or presses, enhancing its strength and durability. And the last one is extrusion. The steel is forced through a die to create long shapes with a specific cross section.
Heat treatment is a process that uses extreme heating or chilling to change the properties of a material. There are different techniques of heat treatment such as first, annealing. It changes the physical and sometimes chemical properties of a material to increase ductility. Second, quenching. This hardens the metal, making it less ductile but more brittle. Third, hardening and tempering. It strengthens the metal from the surface to the core. Fourth, case hardening. It hardens the surface of a metal substrate while maintaining a softer core. Fifth, carburizing. Involves heating iron or steel in the presence of a carbon-bearing material, such as charcoal or carbon monoxide, to make the metal harder and more wear-resistant. Sixth, induction hardening. Enhances the mechanical properties in a localized area of a ferrous component.